All right, I'd like to welcome everybody to this meeting of the Delaware Astronomical Society for November. We got an exciting meeting today for you all planned out. So the first thing I'd like to do is welcome any new members. Do we have any new members this evening? Nobody? Okay, cool. Anybody interested in being new members? You guys excited?
Maybe. Yeah. Don't know yet.
That would be these guys over here. Welcome. Thanks for coming. Thanks for coming. Very cool. And welcome back. Nice to see you again. All right. So first thing on the agenda for this evening, Bill, did you have anything for the AP Sig? Is he here?
Yep.
Yeah, there he is.
Yes, the next AP-Sig meeting will be Saturday at 1 p.m. on Zoom, and the announcement will go out via groups.io probably Thursday.
All right, so next item, Mary, can you give us a little update on the book club?
On Thursday, the book club meets at 7 p.m. via Zoom, and we will be discussing the Michael Frayn award-winning play titled Copenhagen. We selected the play to mark the 100th anniversary of Niels Bohr's Nobel Prize Award in December. We are really delighted that Professor Mark Walker, who is the chair of the history department at Union College, will be joining us. Mark is an expert in not only modern German history, but he's also an expert in nuclear history. If you have the DVD of the play Copenhagen with Francesca Ennis and Daniel Craig, the Bond actor, at the end they have a BBC documentary, and Mark is interviewed in the BBC documentary. I corresponded with Christian Boas at the Niels Bohr Institute, and he said that we will have a fabulous meeting with Mark. He is very respected by the Niels Bohr Institute. The archivist at the Niels Bohr Institute also sent us links to primary research documents, which document the correspondence between Bohr and Heisenberg, and this very controversial 1941 meeting, and exactly what was said and the import of that particular time period. So I hope everyone will be able to join us, even if you've not read Copenhagen. I think you can watch it online. You can listen to an audio version. I've sent everybody a link to that. If you need any of these links, please reach out to the dasbookclub@gmail.com. In December, we will be reading this book, Public Astronomy, LA Style. They want some squares from Delaware to review this for the history of the Journal of Astronomy, and which is a great honor for us as a book club to be asked to review a book that was put together by the director of the Griffith Observatory, which is one of our most respected observatories in the United States. It is a really fun and beautiful book. You can buy it online at the Griffith Observatory. It's chock-a-block with illustrations and photographs, and shows really the role of amateur astronomers in the vibrant scientific world out in LA, that we're developing and at the same time in tandem with this incredible professional scientific community. So it's a really interesting read. It's a series of essays, and it shouldn't be a long read. So anyone in the club who would like to read it, particularly I'm interested in connecting with anybody who spent time out in LA and has experience with the LA public astronomy style and could weigh in. That would be of great import. And finally, I just want to announce that Professor Shrimplin from Gresham College in England will be joining us in January as we celebrate the 300th anniversary of the death of Sir Christopher Wren, who was known, I guess most people associate him with St. Paul's Cathedral, but he was also an astronomer. And she has written a beautiful essay, which she shared with us for free, I've got the PDF file I can send to you, and it is on the subject of Wren as both architect and astronomer. And so that should be another really meeting. Thank you, everybody. Look forward to the meetings and hope you can join.
Nice. You always get very exciting things going on in the book club. That's very exciting. So the other thing that I'd like to update people on is that Gary is working really hard to take the focuses that I digitized a few years ago and redact information so that they can be included in some of the local libraries, so that it can be publicly accessible for people to use for doing research and for archiving historical documents and sharing them for people who are doing research into astronomy or the local history. So that's pretty exciting. So she's going to redact addresses and phone numbers and personally identifiable information like that. And also, if anybody has a picture or anything they're concerned about, because originally, you know, it was a limited readership and now it might be a broader readership, you can contact Mary about that. Again, everything is currently accessible to any DIS member. You can read all the focuses back to the founding of the club. They are on the website. If you have a login, you can take a look. And if you have any concerns, you can contact Mary. Second thing, in conjunction with that, is Mary is looking for some assistance in redacting that information so that it can be sent to those other institutions. So if anybody is really excited in archiving history or saving some of the history of our club, we have a very long, detailed history with all sorts of exciting things that we've done over the years. And so if you have any interest in history, by all means, contact Mary and give her some assistance, and that'd be really great.
Thank you. Thank you, Rob.
Certainly. So next item on the agenda, Bob, do you want to say anything about the membership drive?
Yeah, we've begun to start collecting dues for 2023. 59 members have renewed. 60 members have renewed.
Can
I see 60? We really appreciate you know, the dues go a long way to making the club successful. If you haven't renewed yet, you should have gotten an email from me yesterday that you know, reminded you that dues are due, and there's a bunch of different ways you can pay. You can pay in person in a meeting like this, which we're having in-person meetings now again, or there's various PayPal links, or you can mail me a check to my house. That's all in the email I sent. It's also in the first page of the Focus this month. So if you can't find my email, just go and look at the first page of the Focus. It has all the information. Again, thank you for paying your dues.
And thank you, Bob. Excellent. Next thing I wanted to announce is that coming up next month, we're going to have the exciting holiday party and swap meet. And for that holiday party and swap meet, it'll be here live at Mount Cuba. We will not have a speaker. It's just going to be cool festivities. So there's going to be a lot of items out in the hallway for you to peruse that are currently owned by different DAS members, and you can purchase it for yourself if they're willing to sell it. The other thing is the club has a number of items that we would like to put in that sale as well. And we have some items that are higher value that we would like to have a silent auction for. So it's going to be very exciting. There will be lots of details and pictures and information about those items in the next edition of the Focus. So get really excited and pepped up for that holiday party. Also note that the food at the holiday party is a potluck, and you can bring sweets, but you can also bring savory dishes because we can have dinner. You know, for years and years, it was all just holiday sweets. And
No,
it was too much.
no.
But it was really nice the last couple of years because we had chicken and we had lasagna and we had all kinds of good food. And so we encourage everybody to bring out all sorts of food, and we'll have a nice big holiday bash.
Yeah.
Anything to add?
And just another, so, and actually in December, per normal, we will not be holding our board meeting that month. And so the meeting will officially start at 7 o'clock, but it's a casual meeting. People are welcome to come and go kind of whenever they want. And obviously keep an eye on the groups.io as well as the December issue of the Focus for additional details. And just, you know, just to maybe clarify a little bit about the swap meet, again, it is an opportunity for club members to get rid of any gear that they don't want. You can get rid of it however you want. give it away, put a price on it, auction it. It's really up to you. We will provide tables for you to put your stuff on. And also, if there's some stuff you might want, come and keep your eyes open. So it always ends up being a fun time.
Guys, when will the gate be open for the Christmas meeting?
So
I would.
It'll be open at 6:45 because the meeting starts at 7. So I'll get
Yeah.
here before 6:45. The members should show up after 6:45. And then at that point, you can certainly come on up and have a good time.
Yep.
Great.
Any other announcements that people have that I missed? I think we got everything. We can
Well,
proceed.
I got one other one.
Oh, one more?
Yeah. I mean, while we're talking about meetings, just
Sure.
I know it's a little ways out, but at the board meeting, first of all, thank you to everyone that responded to the dinner meeting survey. At the board meeting that we just came out of, the board decided that at this point, we will proceed with planning for a May dinner meeting. Seemed like it was overall very favorable response, and it sounds like the majority of people are very excited to resurrect the dinner meeting. So we are gonna, it's usually January that we start planning that and putting all the different pieces together. But again, bearing any other foreseen or unforeseen circumstances, at this point, it looks like we will be holding a dinner meeting more or less the same way that we held it the last couple of years before COVID hit. So
Are you gonna be the chef again?
why not?
Very nice, very nice.
Yeah, and to clarify, because it's been so long since we had a dinner meeting, there may be, well, not maybe, there's probably a number of members that joined the club since then. If anyone's curious about the dinner meeting, just ask, you know, a lot of members went to it. If you can't find any member that's been, I would venture to guess that all of the board members have been to at least one. So ask about it. It is a nice event. But you know, again, we'll start planning for that, and you'll start seeing announcements and specifics probably more like in March. But we will start planning it pretty soon.
Very nice.
Jim, did you have something?
Well, I was going to say, I loaned my electronically stabilized binoculars 2 or 3 years ago to a bird watcher, and I can't remember who it was.
Oh,
So
my.
If anybody has one they'd like to sell, I'm in the market for buying.
Ah, did you loan it to a club member, Jim?
No.
Oh,
It was a bird watcher.
got one of them. Gotcha.
Okay.
Always stand outside and just look. Well, actually, he gave me he loaned me his binoculars, which I'm stabilized.
Gotcha.
And now I can't remember who it was.
Right. So you're looking, I will put something for you in the groups.io, soliciting that you could use one.
Okay.
Have you picked any kind of a venue?
What's that?
Have you picked any kind of a venue?
I mean,
Yeah.
it'll likely be back at the church where we held it the last
Yeah.
3 years.
Uh-huh.
We haven't
Yeah,
secured
yeah.
that yet, but you know, that's our first choice at least.
Yeah, yeah, it's a good place.
Yeah, it's worked out really well.
What is it? Christ 100 Episcopal Church in Greenville.
I think it would be called, yeah.
Yeah.
That's it.
Yep, absolutely.
Great. Good question, Edie.
Anyone else with any announcements? I think we covered everything. All right, you're on.
Right. So enough about meetings in the future. Let's talk about the meeting today. What, you know, people actually came out for. So this month we are joined by Henry, who is actually a very interesting story, and I'll really put him on the spot and embarrass him a little bit. After a long career in engineering, correct?
Yes.
Henry retired. And like most people do when they retire, Henry decided that he would earn a PhD in astrophysics. So like, yeah. So I think he and what's the guy, Brian May from Queen, were in class together.
He's a little young for me.
Yeah. So Henry is pursuing a PhD under the advisement of Judy, correct?
Yes,
Awesome. And how far into it are you?
it's my third semester.
Oh, yeah, so you're just getting started. Cool. So yeah, so that's really awesome. Henry also has some other interesting hobbies. For a couple of decades, he's been a goat farmer. So I'm sure if that piques anyone's interest, if Henry will be hanging around after the meeting, you can talk about astronomy or PhDs in astrophysics or goats, whatever strikes your interest.
Mark has donkey.
Yeah, there we go.
We got rid of ours.
You used to have some. That being said, after the meeting, there will be refreshments. So for people that are interested, welcome again per usual, hang out, chat, enjoy some great refreshments. Want to thank Chris Horrocks again. While Diana Mesker's recovering from surgery, Chris filled in for her. So again, we've got some great refreshments to snack on, because doesn't look like we'll be opening up any telescopes tonight. So with that, Henry
might launch.
what's that? Yeah, yes.
1 o'clock tomorrow morning.
Yeah, do you want to say 30 seconds? I mean, I guess that's about it. Yeah, let's keep our fingers crossed for Artemis. All right, with that, bear with me, Henry, we'll get you all loaded up. So yeah, so tonight we are joined by Henry Sanford-Crane, who is going to be talking to us about the life of the sun. And again, I guess I need to do the sharing, right, Rob?
Yeah.
And I think I'm almost remembering how to do it. Screen's probably the best.
Yeah.
Come on. There we go. And we'll change this to speaker view.
Oh,
Whoop.
mute the people there.
Oh yeah, that's right. I'll get this one of these days. Except now I can't. Let me just stop the sharing. Yeah, so again, Henry, a couple of protocols. Again, we kind of leave it up to the speakers. If people have questions, do you want them to interject, hold them till the end?
I want them just to jump right up and ask me questions. And if we go sidetrack, it doesn't matter.
Okay, fantastic. So just to keep the audio nice, I am going to mute all of the Zoomers at this point. But per Henry's request, if anybody has a question, unlike the way we did it when we were fully, just unmute yourself. No one's going to be, I'm not going to be monitoring the chat window or anything. So if you do have a question for Henry, by all means, at any point, just go ahead and unmute yourself, ask your question. Just please remember, once the question's done, to go ahead and remute yourself again to keep the audio really clear. And please remind me where that is. Here? Participants. Nope. Is it here? Rob, how do I mute everybody?
Bring up the participant window.
This?
Yeah. And then mute all of them.
Yes, and that doesn't mute me, right?
No.
Okay. Whoops.
And-
I'm saying,
That concludes my talk.
just hit that again.
Yeah.
How do I get rid of this?
No, we'll go.
Okay. Oh yeah, you think I have, we've not been doing this for the past 3 years, but
There you go.
all right. Yeah, I think it will once. Hello? Why is it not switching over? Hello. Hi, what's going on here? Can it?
There you go.
All right, Henry, sorry for my
No problem.
clumsiness. The floor is yours.
All right.
Everyone, welcome, Henry.
Thank you. As he said, my name's Henry Sanford-Crane, 45 years as a chemical engineer. Worked on all sorts of fun projects. Instead of buying woodworking equipment to retire, I decided to go back to school and get a PhD in astrophysics. Today I don't know, didn't get much information on what kind of talks you want, so it may be too technical or it may not be technical enough. I don't know. I think
Probably all of the above, depending on the
probably
person.
depending on who you are.
Yeah.
But we're gonna call it today. I would like to talk about a star that's pretty close to us. You've probably seen it once or twice if you looked out in the night sky. Well, probably not the night sky. You might have seen it out there. So what I'm gonna do is cover from the sun from today to about 95 million years from now. Oh, not million, billion years from now. Big B. Okay, where's the?
What are you looking? Oh, yeah.
I have to go over here.
Wherever you're more comfortable. Yeah. I mean, does that work for you?
All right, so the sun, we assume it's about 45 billion years old right now. Okay, it's a pretty good size. It's 109 times larger than the Earth. These are just some relevant facts. It's 300,000 times heavier than the Earth, but it only weighs a little bit more than water in density. It weighs about the same as Mylar. If any of you guys worked at DuPont, you know, that's one of their big products. And plastic. So basically, it has the same density as plastic. So for something that massive and that heavy, it's not very dense. It's bright. Just imagine 1,000 watt, 100-watt light bulbs all close together, about 3 meters away, 10 feet away. Kind of blinds you. So it's just the sun, pretty straightforward. This is, you guys are astronomers. This is probably your chart. This is your slide. Okay, the sun is on a main sequence, we call it. These are stars that are burning hydrogen normally. It's located about here on the main sequence star. It's going to eventually change. Over here on the your far right is the from Gaia. It's the telescope that's been up in space telescope that's been up there. It's been monitoring the sky. It's collected over 150 million. No, yeah, 1,500,000 stars it's cataloged so far. Of those, about 100,000 have been white dwarfs. You can do I made this diagram, which it is a density profile. So the brighter the color, the more yellow, it means there's more star in that location. So you can see that this cartoon is actually showing up in real life. All right. So just the HR diagram, I think you all familiar. Please, if you have any questions, go through. Okay. And I'm going to use the term luminosity, which is just how much energy does a star put out. You guys have probably used the term absolute magnitude. Well, that's derived from here. So we're going to use that. The luminosity just tells you how much energy the sun is putting out any day. Okay. I made a timeline. It's kind of small print, but I was working on it. What I wanted to do is, most of us aren't really familiar with 1 billion years or 100 billion years or even a million years. Kind of gets confusing, but we're all pretty familiar with a year, a calendar. So what I did was I took where we are today, when the sun was born, and calculated a timeline based on last January 1st being the first day of the universe. Okay. And so the sun was born on July 29th. Okay. So the universe was already 7 months old before the sun even was born. Currently it's middle January, November, and we're here. Okay. So I'll have this timeline up so we can see how quickly things are occurring. Okay. And of course, I said that already. We normalized the amount of light coming from the sun right now is going to be my norm. What I look at everything for, everything's going to be, that's going to be 1, and everything is going to be based on that value. All right. So if most stars in the main sequence are very stable, okay, by that they don't change very quickly. They're going to be slowly evolving. And what causes that is there's some really straightforward physics. There's a hydrostatic equilibrium, it's called, which is the pressure of the gas is pushing outward and gravity is pulling inward, and those two balance each other out. So we end up with that. But because of this, you can derive that the pressure in the center of a star is determined by how massive the cloud it came from, how much mass came into the star. All right, and then any chemical engineers out there? Any engineers?
Yeah, there's a couple.
Yeah, I'm a chemie. PV was NRT. Yes. All right. So ideal gas law. That's, if you're a chemie, that's just something you live with forever. And so this is the ideal gas law that says how gases behave. That comes into it. And the other thing is any energy produced in the star has to escape. Okay. It doesn't hold extra energy. So you put these all together, and every star out there, including the sun, falls into a simple equation. All right. How bright the star is. So when you're looking at the night sky and you see a star and you calculate the absolute magnitude, from there, if we measure the temperature by looking at the yes, whatever, we can get a temperature from the temperature and the brightness of it. We can tell you how big the star is. That's just going to come out naturally. Okay, and this little, the symbols on the bottom, that's, we use the sun as our normalizing factor. So, you know, instead of saying something's 10 to the 30 power grams, we say it's 1 solar mass. Makes it easier. And so all these equations derive down like that. And so this equation is going to tell us what happens to the sun for the next 12 billion years. Right?
I don't even know what I'm gonna do next week.
Okay. So as I said, the pressure pushing outward has to hold the gravity inward. While there's some energy has to produce that, we know that the sun is a nuclear furnace. It's taking hydrogen atoms and it's fusing them together, producing a lot of energy. And you can say, wow, how much energy does it take? Well, it turns out the amount of energy to hold the sun in its current size is only 0.034% of the mass of the sun. So very, very little mass goes into keeping the sun, the energy of the sun coming out of the energy at any one time. Even though, if you guys know this number, that's a huge number of joules. A joule is equivalent to a watt. So that's a ton of power, but it's only the total power you need for 5 billion years is only a very, very tiny bit of it. So we could say, well, maybe the sun will live forever because it can just do that. Well, it doesn't work that way. So what happens is in the center of the sun, the core is very, very dense, very hot. It's hot enough for the hydrogen atoms to fuse together. Okay, to do that, it has to be about 15 million degrees Kelvin. So it's very warm. But only in the core of the sun can that happen. So we need to know how much material is in the core of the sun. And we can go through all this calculation and pretty technical, but we can see that for every 4 hydrogen we have in the sun, we produce 1 helium, and it converts 0.07% of its mass. And so, but we're going to be burning hydrogens faster than we're losing mass by far. So it's not a question of how much mass I have. The question is how many hydrogen atoms do I have to fuse together before I run out, before I stop producing energy. And you just do some little math. Einstein's equation, of course, we all know, equals mc squared. So we're going to get 5 billion years, and then all that hydrogen in the center of the sun is going to be turned into helium. Okay, and then the fun starts. Okay, and that is next April 15th, tax day.
Nice. Nice. I don't have to pay taxes that year.
I paid its taxes. It's out of money. It's done. So we can see that we got about 5 billion years. So on tax day, it's going to run out. It's not going to immediately realize it's poor. You know, it's still got some food in the refrigerator. It hasn't, the monthly bills haven't come in yet. So it's still going to go on a little bit. And the way it's going to go on a little bit is when it runs out of hydrogen in the core, that's going to continue to collapse and it's going to get hotter. And the outside of that material is going to get hotter also. It's going to get hot enough so that there's a ring of hydrogen and will catch fire. Will start to fuse around the core. And that ring will produce even more energy than the core did when it was burning. Okay, so it's going to produce more energy. And the sun, okay, so now we're producing more energy. Remember, I told you the energy out has to equal the energy in. So we're producing more energy. So all of a sudden, the sun has to do something. It's going to start to slowly. It's going to grow. Okay, and it's going to grow, and it's going to grow by that formula. Okay, and we can. This is some charts. This is to to be completely honest, I had a presentation in my physics of the sun class, and this is some of this data I had to present for them. Some programs you wrote, it shows you that indeed the hydrogen, this is where the hydrogen's burning, that it's not in the center of the sun, but it's out in the ring of the sun. Okay. All right, so now that it's run out of hydrogen, the ring is burning, and for the next month, the sun's gonna have all sorts of fun. All sorts of stuff is gonna go on in the next month. A month in this calendar is about 1.2 billion years. Okay, so it's not instantaneously, but in terms of this, it's a month is about this, okay? So we're gonna go through the sun's gonna go through all these phases, and these phases, I should have put that chart in there, are just like when you look up and you see Betelgeuse, that's out here in this phase. If you see other giants, they'll be in this part of the branch, okay? This is the path that the sun will follow, and over here there's some other stuff. But so we're gonna show you each one of these color steps, what's gonna go on each steps. So we're right about here. Okay, in the sequence right now. All right, so now when the hydrogen ring is burning, the sun's gonna get bigger and bigger, and it's gonna become a red giant. All right. The way it's gonna become a red giant is it's producing more and more heat, but the temperature of the outside of it isn't changing. In fact, it's going down. Okay. It's producing more, L is getting bigger, T is going down. So for this equation to keep the same, R has to go up a lot. Okay. And it's going to go up a real lot until about 1 billion years after it runs out. It's going to get to about 100 million Kelvin. Okay. So it's going to get very hot in the center. Right. And that's going to be May 9th. Okay, on May 9th, it's not going to be a very good day to be around. Right. There's going to be a helium, what we call a helium flash. That's the core. I'll get to it, but the core is going to get really dense because more and more helium falls into it. We call it ash. You can imagine helium being an ash because it's inert. Right now, it's not being fused, so to us, it's like a burnt material. What's left over when you burn stuff? Ashes. So the ash falls into the center, making the center denser and hotter. Gets denser and hotter. It's going to get to 100 million degrees, and then something's going to happen. All right. But before that, just before that, all right. The sun is going to get to 1.2 times 10 to the 8, 120 million degrees Kelvin. Pretty warm day. If you were Venus, you'd be right here in the middle in the sun. Okay, and you'd be about 12,000 degrees. Venus, you think Venus is warm now, but on May 9th, it's going to be very warm. And we can see that the density is very unusual to have this much. This is the R stands for the radius of the sun based on an initial value of today's sun of radius 1. Okay, so this says that the sun is almost 200 times bigger now at the just before the helium flash than it was today. So it's huge. Okay, and close as you see, it encloses Venus. Okay, and it's going to be 4,000 times brighter than it is now. Some models say it's going to be almost 8,000 times brighter. So it's going to be a pretty bright day. It probably won't be much fun to be on Earth. Probably be pretty warm then too. But helium flash. So the core has all this stuff helium built up in it. It's getting hotter and hotter. If we all know like opposite like charges repel each other. So if I'm taking a helium atom and another helium atom and I try to get the nucleuses together, they're going to push them apart. Okay, and each one of them has two positive signs, so it's going to push them apart 4 times as hard as 2 hydrogens coming together. Okay? It's going to really push itself apart. So to get them to coming, I have to have them moving really fast so they can get close enough so that they'll fuse together. And to do that, you have to have this really high temperature. And once they start, this whole core, because it's more of a liquid than a gas now, behaves like a liquid. And we know when we're boiling water in the pot, the temperature of the water is all the same. You know, there's not cool spots, but we're as a room, like we're gas in the room, you got cold spots and warm spots, and it's not very uniform. But here it's almost all uniform. And when it gets to that magical temperature, first a little bit of it fuses, produces some heat, and immediately more fuses, and immediately more fuses, and immediately more fuses. And within 30 minutes, the sun will release more energy than it has in its entire lifetime.
Is that 30 real minutes or?
30 real minutes.
Okay.
Right? Not calendar minutes, 30 real minutes. Okay, that's how quickly this happens. All right. And you go, geez, I'm going to be around. I'm going to go to, you know, maybe Alpha Centauri, set up my telescope there and look at the Earth. Okay. And I'm going to say, I'm going to look for this flash because it's going to be spectacular. You're not going to see it. So what happens is the core is very, very dense. And it's in the state we call degenerate matter. It means it's tighter together than you can imagine. But when it flashes, all that heat goes into expanding the core. Okay, none of that energy goes outside the sun. None of it goes out to the atmosphere of the sun. None of it goes out there. All it does is expand the core. Okay, it takes it from degenerate matter to regular matter. And chemies know PV equals nRT now starts over again. So you're not going to see it from a distant star. There's a telescope being put up down in South America called the Vera Rubin. You guys might have heard it, or LSST. There's some people are trying to figure out how can we look at stars and find helium flashes. Is there any signal at all? We're hoping that maybe we can come up with an algorithm. So some of the data from the Vera Rubin we'll see a star go through a flash, but the likelihood is very high.
I have a question.
Sure.
Why is it that all that heat does not get out of the core? Is it because it's just
Okay,
it's so undense, if you will, and there's nothing to?
It's kind of like when you have a pot of water boiling, as I'm heating up that water, I'm putting a lot of heat into that water, and it's not getting, the heat's not going out into steam. The water is just getting hotter and hotter and hotter. And then it changes from water to steam.
Okay, yep.
And so basically we're changing from degenerate matter.
Oh, okay, so it's the state changed it.
It's a state change, yes.
Okay, gotcha. I
Okay.
got it. Thank you.
All right, so now we're still on the May 9th, okay? All of a sudden, the luminosity of the sun drops a lot right after the flash, okay? When it flashes, it burns so much helium all at once that there's not much left to burn. So now the temperature, because it all went into expanding it, it's not burning very much. So now the luminosity goes down. The gravity starts to pull it back together a little bit. And it drops down, okay? And then a couple days later, 3 days later, the weekend, after the end of the weekend, it's going to be another red giant. And I'll go through that next step in a minute. All right, so right after the flash, it's going to settle into what they call a main sequence helium burning. Okay, all the hydrogens are gone, but the core is now burning helium at a pretty fast rate. Helium burns when it starts, it burns much, much faster than hydrogen. So going to make more energy quicker. More energy quicker means the sun has to get big again. Okay. But this time, instead of just burning helium, this core, the helium is producing so much heat that the outer layer is heating up, which is hydrogen. And so now I'm going to have a core of helium burning and a ring of hydrogen burning. So I got two sources of energy now. And so it's going to even get much bigger. And every once in a while, this helium is burning outward will run into the hydrogen ring. When that happens, it burps. It stops producing energy because the helium needs fresh helium, but it catches up to the hydrogen. So it doesn't have fresh helium, so it turns off for a second. And we get all sorts of fun patterns. Okay. And we can see this is some information. We can see that the radius of the sun went from 200 down to 12 after the flash. It went from being a red giant, then it shrank right back down real quick. And we're at this stage here. And these are the burps we're going to talk about. And the last chart over there, we can see that there's two places where it's burning. Where it goes up means it's producing energy. Where it level means it's not producing energy. So you can see there's two steps.
How long does the flash last?
The flash lasts about 30 minutes, real time. Okay.
Is that what they call a nova or?
So it's very similar to that. So it's like a micronova. Okay. A nova would do about the same, but the amount of energy would be 1 million to 1 billion times more. Okay, and it would be enough to blow the star apart instead of just puffing it up a little bit.
Have any of these flashes been observed?
Not yet, no. We're hoping to be able to find one.
So it goes through 2 helium flash cycles. And
Yeah, it goes through a helium flash, and then
red giant,
it goes to red giant phases,
red giant.
but no more helium flashes.
Is this typical of the stars or just the sun?
Depending on the size, if you're 8 solar mass
Yeah.
smaller, you'll go through a cycle like this. There might be an extra cycle, but you won't. But if you're more than 8 solar masses, instead of you're going to go through this cycle, and then when you make helium, you immediately start making carbon. When you start making carbon, you're going to immediately start making oxygen. Then you're going to make neon, and then you're going to make iron, and then the whole thing is going to blow up into a supernova.
So this is a much shorter time frame versus the hydrogen.
Yes, the hydrogen lasts 10 billion years. This whole helium burning lasts about
Helium to carbon is,
helium to carbon is the flash. Most of the helium went to carbon. Okay.
So that ring, or I imagine it's actually sort of a.
It's a sphere, yeah.
Okay, of hydrogen, why doesn't that use?
Before, because it's out, it's like, as you know, when you get further away from the Earth's surface, the atmosphere gets colder.
Mhm.
So the atmosphere of the sun is cooler at the surface than it's in the middle. Hydrogen needs to be at 15 million degrees. to
So the
produce.
heat from the helium flash isn't enough.
So that heat went all into making it bigger. It didn't go up into the hydrogen.
Okay, got it.
Okay.
so did Betelgeuse go through something?
Yeah, Betelgeuse. We believe it went through a burp.
Okay.
Okay, right now, that's the best guess. It could have been a precursor to it going some other step, but we think it's just a burp.
And greater than 8 solar masses means that it could be a supernova?
Yes, if it's greater than 8, so what happens is, this is a good topic. So when the sun turns into a ball of helium, if it has enough mass that the core gets denser and denser, okay? And I talked about a little bit about degenerate matter. Degenerate matter is when stuff is being held apart by electrons. the nuclei aren't being repulsed anymore. It's, you can't fit any more electrons closer together. So that's a quantum effect, and it keeps the electrons keep the gravity from squishing it in. However, if you're more larger than a certain value, and I'll get that value in a minute, the mass is enough so that it goes through the electron degeneracy, and the stuff keeps getting squeezed closer and closer together, getting hotter and hotter, and that makes carbon able to fuse. And once carbon can fuse, it turns into oxygen, and once that can fuse, it turns into iron. And when you hit iron, iron is a sink. Iron has to go from iron in any direction, if you get bigger than iron or smaller than iron, it takes energy. Okay, so iron is the end game. Once you get a little bit of iron, the heat turns off, it doesn't burn anymore, and everything, it collapses even more. Once you get beyond you're already beyond electron degeneracy, and to collapse even more, now you're forcing neutrons to pair up, you're forcing electrons to pair up with protons to form neutrons. Okay, and when that happens, that releases a ton of energy, and you end up with a neutron star. And then if it's like 10 solar masses or 12 solar masses, it continues to collapse because neutron degeneracy has a certain force. But if you're even more massive, then that collapse gets pushed together and nothing stops it, and it turns into a black hole.
What form is the iron in? Is it a gas?
Yeah,
Iron vapor.
it's a plasma.
Okay.
So it's just going to be an iron nuclei and a bunch of electrons floating on.
What is it about iron that makes it unique in that sense?
It's a
Dead in middle.
yeah.
But why, I guess, is
Well, if you look at it, you got a hydrogen is a single, helium's got 4 things on it. Carbon's got 12 total,
Mhm.
you know, and the configurations of those, you can just pack iron just right in the nucleus so that it has the lowest nuclear energy.
Okay,
Does that make any sense?
a little bit, yeah.
So like hydrogen can, per unit, hydrogen's pretty active. Helium's less active. The next one's less active. Iron is perfectly suited to be packed perfectly so that you can fit the most stuff in the least amount of volume. It's not, that's the analogy I'm going to use.
Sure.
So you try to put any more in there, you're going to destroy the packing job, and it doesn't fit together anymore. So once you get the iron, the nucleus is perfect. Okay,
Gotcha.
you can't get
I have a question. This might be Delaware, but how
No.
much of all of this has been observed?
all this has been observed. That's the perfect astronomy question. Okay.
And if so, or if not, how do you know your model's accurate?
So where we get how do we know it's accurate? Some basic physics we believe is accurate. Okay, we can say that might not be right, but where we get most of our fact finding is from astronomy, not from astrophysics, but from astronomy. Okay, we get, like, you could question me, does the sun burn? Is the sun fusing hydrogen? Right, that's a big leap. Well, physics says, well, if you're burning hydrogen, it should be producing a thing called neutrinos. Neutrinos are very, very low mass. There's trillions of them going through this room right now. Okay. Can we see them? Well, no, they don't interact with matter very much, but they've done experiments where they take chlorine atoms, and chlorine atoms, when they hit by a neutrino, once every 100 years or a billion years, that will turn into an argon atom, and then that argon atom decays and it gives off a certain light. We can observe that, and they've done the experiments, and they show that the amount of neutrinos coming from here follows the model that I showed earlier, and that, yeah, now we can say, yeah, we're pretty sure up until It was about 1960 when a guy named Davies got a Nobel, he ended up getting a Nobel Prize for it, found neutrinos. And up until that time, we were just thinking, we didn't had a theory, it was nuclear burning. So we go through these things and we start to say, okay, in a model, how many of these Betelgeuses should we have at any one time? Okay, we can say it takes this long for a star to burn through its hydrogen. And once it burns through its hydrogen, it should turn into a red giant and it should last this long. That means on an average, when I look up in the galaxy, I should be able to count this number of red giants. Okay, if I see many more red giants than that, then my theory is wrong. If I see what less red giants than that, then my theory is wrong. Right now, especially with this data, as we get more and more data, it's showing that the theory is pretty good. It's predicting, if I say, I predict this number, I'm getting that number. That's how we think our theories are right. We've done some other math, you know, the math seems right, other stuff seems right, but that's all I can say. Other than that, but astronomy is really our friend and our curse. Because we can come up with theories and you guys,
Well, what I mean is Betelgeuse has always been Betelgeuse from what we can see. It hasn't just moved into Betelgeuse.
right,
That's what I'm saying.
right, so,
Like, you know,
so we don't know that.
I mean, that's just.
I mean, we could say
They've
that,
all been there.
we could say that yesterday someone came
Didn't see
and
them.
populated the universe looking exactly the way it was. Or we could say, looking in this room, we could say that humans are born 50 years old or older. Right? Just look at this room. That's
I think offense to that.
there's a few exceptions.
You know, with outliers.
There's a few exceptions, but you know what I mean, there's no such thing as a baby. We can't agree. So the way we look at it is we can't say that if you just look at this population here, you can't say that there's things called babies and that there's children and that they grow up. And if I take a snapshot of someone's apartment and I only look at it once every million years, when I look at the apartment, they may be in the bathroom. And I could say, oh, humans, all they do is go to the bathroom. You know, because that's, so what we have to do is, we know it's a snapshot in time. And we know this snapshot in time is Betelgeuse in its time. This snapshot is all these stars. And we start to say, how do we make sense of all these things in a row? How do we, if we took a picture of a baby, a 3-year-old, a 5-year-old, from different ages of the earth, we can say, they all look alike. Maybe those are humans that are growing. We can say, maybe these are stars that are going through this phase because we have a lot of them. That's all we can do. Okay, we can just look at snapshots and make prediction that the snapshots are telling us about the lifespans of stars.
Have astronomers observed a number of Betelgeuses? This isn't.
Yes,
the only
yes,
one.
yeah. These are, so Betelgeuse is right here, and that's probably 10,000. And this little patch right here is probably 10,000 stars.
We have a pointer right over there.
Oh, sorry.
For it.
In the marker tray behind you,
The stick behind you.
behind you.
Behind you.
There's a stick.
Yeah, they're the old time.
Yeah.
Yeah, you got it.
You're looking right at it.
Oh, this guy.
Yeah.
Yes, that's what it is.
No batteries required.
Okay, thanks. All right, so does that answer your question?
Yeah.
Right, you can ask more. I mean,
It's kind of philosophical. Yeah, well.
it really is. So we're,
The spectroscopy.
all we have is today. Okay, we take pictures of the sky and we're trying to deduce what do we know about the sky. And that, you guys do that. You look up in the sky, you see stars, and don't you wonder why is this star bright blue and this star red? And then we said, oh yeah, I do wonder about that. And so we go out and say, I can look at the spectrograph, the spectrometer, whatever you want to call it. I haven't seen that word up. But I can look at the spectrum of the light. And I can see hydrogen lines, and I can see lines from helium, I can see lines from different compounds. And I can tell what temperature that atom is based on where those lines are. Okay, that I can do in a lab at Delaware right now. I can take an atom and heat it up and do the spectrometry and say, that's the temperature. We do it when I was a chemical engineer, we take images, spectral images, and say, this is my compound. That is really well understood. We do that with stars that are 13.4 billion light years away from the most recent JWST. And we see hydrogen in it. And we see hydrogen at temperatures and stuff. And so we know that this Rigel is a very, very, very hot star. Okay. We know Alpha Centauri is a very cool star by looking at the spectral lines in it. So we can get a lot of information by just looking at it. Now, nobody knew this. And these guys, the HR stands for Hertzsprung Russell. They put this chart together. They took stars and they started plotting them on a line. And now somebody found this band of stars here, and they go, why is that? And then people start thinking about, oh, maybe it's how massive they are. And so they got some more information, and they found that Alpha Centauri isn't very massive compared to the sun. They found Rigel is much more massive than the sun. And we can do, how do we find out what the mass of a star is?
Weigh it.
We weigh it. How do we weigh it? That's the best way to weigh. So the best way to weigh something in space is measure another body circling around it. Gravitational orbits. Okay, you know. Who's the formula?
So is Rigel burning hydrogen?
Yes, it is. Very fast. Okay, it's going to have a very short life. Guys ever watch Blade Runner?
Yeah.
Remember that last scene where the guy says, we live fast, we live a great life, but it's very short. That's Rigel. That when I heard that line, it was like, oh, you're a super massive star. But that's the best we can do. I mean, we'd love to be able to go in a time capsule and study one star for 10 billion years and then come back and report what happened to it. All right. Hydrogen runs out, luminosity, having fun, bad day. Okay, helium flash. So what's going on in helium? The helium is going to get together. It's going to form carbon. Ultimately, the carbon from this is us. Okay, from previous stars that have gone through helium flashes, most of the carbon in the universe comes from helium flashes, and I'll show you in a few minutes how it gets into the rest of the plate and gets spread out. Okay. All right, so okay, we got the rings. We're going to have a burp, and we're here, and then we got perfectly sidetracked because I loved it. All right, so once eventually all the helium is going to get spent, it's going to be almost dead, no more burning. The sun is going to be very, very large now. Okay, it's going to be extremely large, and there's no more helium. The cores continue to collapse, but there's not enough mass for it to go degenerate. It's going to go degenerate before the carbon can set fire. For carbon to fuse, it has to be 500 million degrees. Okay, the sun right now at this time in its life is about 1.2 million degrees. 120 million degrees. Okay, I always do it 1.2 times 10 to the 8, but try to use real numbers. All right, so we can see that at this planetary nebula phase, can anyone remember on my first slide when I talked about the sun? How far was the Earth from the sun in radiuses. I think I mentioned it. 215. Okay, where's 215 on this chart? Right about here.
Mhm.
So at this time, Earth is going to be at 11,000 degrees.
Hmm.
And it's going to be incorporated into the sun. So it's not going
Global
to be,
warming for you.
that's going to be a global warming.
Yeah.
Yeah. But you can see though, the maximum temperature is only going to be about 2 times 10, 200 million degrees.
Yeah.
It needs to be 500 million degrees for carbon to fuse. So carbon's not going to fuse. But we're also going to see here that most of the mass of the sun now has collapsed. And it's all within 1/100th of the radius of the current sun. And the sun has lost about 40% of its mass to the nebula that's going to be formed. Oh, did I miss that? You guys recognize this one? Ring Nebula. The sun, the best model says it will be, get rid of all this beautiful red, get rid of all this purple, and it'll be just a little small thing. It's not going to be as pretty as the Ring Nebula, but it will be a red nebula. It'll be one of the smaller nebulas around.
Was this a larger, like, what was different about that star that made
Much
it
larger.
Okay.
Okay, anything up to 5 solar masses. So the sun loses 40% of its mass. This star probably lost, let's see, it went from 5 solar masses down to 1, so it lost 80% of its mass. So it's lost 4 solar masses of material, whereas the sun will only have like 40% out there. So 10 times more material out there than the sun, right? All right, so we can see the other thing, the neat thing, this is, to me, this is a really interesting picture. I don't know how many of you guys are geeky like me, but this goes, you can see that this is the density profile of the sun. You can see extremely dense at the middle, and it drops down, but about 150 away. You can actually, my brain sees this as a wave of material, this flowing outward, away from the sun. You can see that because it's not going to have much gravity there, that material is just going to easily float out, forming that nebula. It's going to be released from the gravitational pull of the sun, and that the sun is now going to now the sun said, hey, that was a fun month, because now it's May 13th. Okay, fun month, ran out on April 15th, May 13th is now, it's no longer has any energy left, it's not burning anything, and it's going to start to cool off.
That's
Okay.
before it didn't.
All right, so as it's good.
We should have it in April then.
Yeah.
Question,
Yes.
you always talk about and I also heard other talks talk about the losing of the mass increasing, but gravity is also decreasing at the same time, as you mentioned. But they always talk about the Earth or the inner planets being developed within the sun. What about gravitational pull? Doesn't the planets basically go off their orbits at any point?
Yeah.
Because of the loss of gravity?
So when we say, I'm saying for simplicity, let's assume the planets are going to hold their orbits, but you're completely accurate that the Earth, since there's a lot of stuff going on, the orbits of the planets are going to be affected. Could it be, and this great debate, is the orbit velocity going to decrease for some reason because of the excess mass hitting it and the energy, or is it going to increase? If it decreases, what happens? It's going to fall into the sun. If it increases, it's going to fly out further from the sun. So nobody really, that modeling is very, very hard, and so no one truly understands what's going to happen to the Earth orbit during this time period. Okay. And most of this is based on as I was saying earlier, on the HR diagrams and what we see from similar size mass objects going up the giant branch and what they're doing. So we're comparing like for like stars. With the JWST now, hopefully we're gonna get some planetary discs. Hopefully we're gonna be able to study planetary disk in red giants. Where hopefully we can start making models based on that data, seeing what happens. And maybe we could answer your question in a few years.
Thank you.
All right. So the interesting thing is the white dwarf that our sun is, it's going to be only 1.125 times the radius of the Earth. Okay, so 60% of the sun's mass is going to be condensed down to basically the Earth's rate and size. So it's going to be extremely dense. The density is going to be 1 million times the density of water. Okay. It's going to be mostly carbon and oxygen. And the white dwarf takes a long time to cool down. Okay, very long time. So if we think about it, if I'm radiating heat, if I'm a big guy, big skinny guy, I radiate heat everywhere really fast because my surface area is very big. If I'm a small compact guy, I stay warm a lot longer because I don't radiate, my heat doesn't get escape from my body as quick. So we can see that the relationship between surface area and mass is really important about how fast we release heat. We got this very, very tiny, very, very massive object. It's not going to release heat very fast. So it's going to take a long time to cool off, even though it's not producing energy anymore. All right. We will go through all this, but we can quickly derive that for any white dwarf, this formula holds. And to get to your question, yes, we know this. This was modeled from some physics. We went and asked astronomers to look for white dwarfs, measure the mass of white dwarfs, and the radius of the white dwarfs the best we can, and it fits this model very, very, very well. So that's where this model was there long before the astronomy, but then now that we have telescopes good enough to see white dwarfs, this model is holding up very well. All right. Here's an HR diagram that I produced from the Gaia data. This is the white dwarf part of it. We can see interesting things here. When this data came out in 2017, first release, someone else spotted this and they see this cume here. I call it a cume. You guys know what a cume is? Any Scottish people here? Or Welsh? A cume stands for a high mountain valley. So this looks like a valley to me, and it's a high mountain valley, so I'm calling it a cume. And but this little there's a valley here, but there's two branches here, and nobody knew what that was. And so someone says, "Well, what do we know about the white dwarfs here, and what do we know about the white dwarfs there?" And they quickly looked at the spectrograph imaging, and they found out these are hydrogen and these have helium atmospheres.
What are the two axes?
This is relevant to temperature. So this is the blue. It's a blue filter. So it's the intensity of the blue filter, and this is the intensity of the red filter. And so when you subtract those two, because of the light curve, blues, if I have more blue, it's a hotter star. If I have more red, it's a colder star. And so when I subtract the blue from the red, the smaller the number, the colder the star. Okay, I can turn that into absolute temperature, but Judy's class does that upstairs with our telescope. So she does this kind of information. We use a couple of filters. By subtracting one intensity filter from the other intensity filter, you can get a really good estimate of the temperature. You don't need a spectrometer to do it. You can do it just by two filters. Okay. So
intrinsically, it's a temperature analog.
yeah, it's exactly temperature. And this is absolute magnitude.
Okay.
So this is that, you know, parsec, how three, whatever, you guys know better than me. How do you calculate absolute magnitude so many parsecs away? How bright it is?
32.6 light years,
Okay, yeah, so that's
10 parsecs.
10 parsecs.
10 parsecs, yes.
All right, so they look at this and they see these is hydrogen, this is helium, and lo and behold, we go, that makes sense now that we think about it. If you have a good blanket on, you're gonna cool slower than if you have a bad blanket. And hydrogen at 10,000 degrees has no electron, it's fully ionized, so it's a bad blanket. Helium has one electron still on it, and so it holds more light in. So it's a better blanket. So the helium cools slower, and the hydrogen cools faster. And lo and behold, all the data says these are helium, these are hydrogen, and things popped up. But in the 1960s, someone came up with a theory that says, if I'm cooling this plasma of carbon and oxygen, cooling it down, it should turn into a diamond. It should crystallize. And if it does crystallize, it should release energy, latent energy. Like, I don't know if you guys, anyone lived up in the far north. The old trick was to take a bucket of water, put it underneath your car engine at night if it's going to get below 40 degrees at minus 40. You put the ice, you put the water underneath your car, and as the water in the bucket freezes, it puts heat up into the engine. Okay. And so as that latent heat, as the stuff solidifies, that latent heat heats up the star, heats up the white dwarf. Okay. Good theory. Up until Gaia, we didn't have any data that supported that theory. Okay. Now we can see, you can see that there's more stuff here than there should be. And this isn't the best picture, but this is what I drew real quickly, that there's more stuff here. And that's if you predict how much latent heat you can get from condensing carbon into diamond and plot that on an HR diagram where it would fit, it fits right here. So the theory says, before I do this, I could have put two lines up there, one where it's 100% carbon, one where it's 100% iron, because those are basically the two extremes of white dwarfs. Where would it fit? And those two lines would come right through here perfectly. And they had those lines before they had any stars in there, any white dwarfs. Now with the Gaia data, we can actually start seeing that this stuff exists. We can say, hey, maybe they are crystallizing. And so what I'm going to be researching is how can we prove that it's truly crystallizing and just not some other phenomenon going on here. Okay, so this crystallization will add a little warmth to the white dwarf. So it's going to slow down the cooling a little bit. And we can see that it actually starts slowing down. This is a model that I created. We can see it starts slowing down. It actually starts warming up the stars. So these white dwarfs are warmer than we expect them to be for the size that they are. Okay. And then on October 25th next year, crystallization is done. No more sources of heat at all. And the sun is now a diamond, basically, sitting out in the sky. And it's got 90 billion years of doing nothing but cooling off. And after 90 billion years, it will be 10 degrees Kelvin, which is about 3 times the cosmic micro background noise. So we could still see it, because it's 3 times brighter than the surrounding space, but not, it's going to be still warm. 90 billion. And to answer your question, no, we haven't seen this because the universe isn't old enough to see this, and there's no stars, no white dwarfs existing anytime soon that old. And that's my talk.
What happens to the oxygen?
Oh, there's oxygen in there. I could tell you it's a carbon oxygen crystal, but nobody likes carbon oxygen crystals. Diamond crystals.
Carbon dioxide crystals.
So you're gonna prove there's big dinosaur in there.
Yes.
Yeah.
I keep my wife.
We had a chart. The golden zone, computational zone, as the sun goes through its phases, that zone pushes out further and further, and encompasses Saturn
Yes.
and Jupiter. Can you bring that slide back up?
Yeah, I have a question for you, Henry,
Sure.
if I may. What conditions have to occur for a star to produce multiple shells in a planetary nebula?
What it's gonna do is, it's just those burps. Okay, so you're gonna go and all of a sudden the core is gonna get, let's say you're gonna get to the helium flash. And that's gonna just do you a little bit, but then it's gonna make carbon. Okay, and then when all the helium runs out, the carbon now can continue to collapse on itself. And then that's gonna go to the next fusion step. And that energy now, because it is not degenerate anymore, it's a gas, not a degenerate. That energy will flash out and that will make a nebula. And then few 100 million years later, or 100 million years or less, it's going to happen again. There's going to be another flash. And so there's going to be multiple burps that create multiple waves of material coming out of the sun, out of the star. The sun probably won't be beautiful like the Ring Nebula.
Is there a specific limit to the number of burps?
Probably, but no, I don't know for sure.
Okay.
You're like my cousin to be a lot.
Depends on when you.
Yeah, so
So in this chart you're showing here,
Mhm.
how much time is in that zone where you've got Jupiter and Saturn? Can life develop in a period where, say, that's
that's roughly 100 million years.
100 million years, which really isn't, it's just.
Probably not enough time. Maybe if, depends when you say it gets there, maybe you get 200 million years, you know.
Okay, that's what I wanted to know. Thank you.
Now, in this case, as the Earth is starting to get swallowed up by the heat of the sun,
Mhm.
Earth's a big rock and it'll heat up and
Yeah.
do whatever it's gonna do. What's gonna be the effect when that heat starts getting out to the gas giants? How's that gonna affect the gaseous planets?
The gas giants themselves will probably have enough gravitational pull to not be affected, but their moons will probably start evaporating. And the moon, the ice will all start to sublime, turn into gas.
Okay.
Probably have some beautiful rings.
Yeah, I
around
was
the
wondering if
giants.
the gas giants would heat up and the gas.
They
would
will heat up,
expand or
they'll expand, they'll get bigger,
something. Okay.
but they're not gonna. They're not gonna probably lose
evaporate.
gravity. They may move out further, they may
Yeah.
be dragged in, depends.
Okay.
Didn't they find a red dwarf that actually had a planet in it?
Yes, they have, yeah.
It's been a big
Well,
surprise.
we won't be around.
That's
Yeah.
another, that's another thing I'm looking at, trying to figure out with Judy,
Oh, right.
is if I have a crystallized white dwarf, and I have a planet, most likely the whole planetary system isn't destroyed. There's still gonna be bodies floating around these white dwarfs. Even though the nebula is out there, that's gonna fly past the planet, some of the planet's gonna stay. But those planets and comets and other things in that will, every once in a while, one of them will crash into the star. And if you crash into a crystal, what happens if you hit a crystal?
Shadows.
It's gonna, well, shatter, but really what it's gonna do is ring.
Hmm.
Okay, it's gonna ring, and it's gonna ring at a frequency that you can predict by the crystalline structure. Okay, and I'm looking at how much of that can we detect. I'm trying to do the math to figure out, can we detect that ringing with a telescope?
Spectral signal.
Yeah, so I would
Line shifting
yeah.
back and forth.
At a certain frequency.
Yeah.
And if we can see that ringing, and if the math is right, then what I want to do is like shine the JWST on one of those that have, like the Vera Rubin will see a flash, because when a comet hits a white dwarf, it's going to flash. It's going to get brighter real quick, and then die down. And when it does that, I want to shine the James Webb at it and measure the vibrational frequency. And when in my previous life, I used to make silicon crystals for a living and used to design them. So I understand a lot about how that works. Now I want to be able to go, look, it's crystallized because here's the ringing and it's this composition and it's this and this much atmosphere around it because the atmosphere will act as a damper. So it won't ring forever. The atmosphere will dampen it. So then you could say what percent of it. And so that's something I want to look at. I don't know if it's possible. We have the telescope capabilities yet, but that's something else I want to look at.
You won't hear the ringing?
No,
Why not?
it's not Star Wars.
They can't hear you scream.
Only in Star Wars will you hear that.
Rob can smell it from a mile away now.
Right. Any other questions? You guys are great, by the way. Thank you.
Henry, I have a question.
Yes.
I'm interested in your computer model.
Yes.
Are you able to conduct your work using a laptop, or is your work predominantly done in the lab or at the observatory?
No, most of my work is done on a laptop or my workstation. But I have a simple model. And so as I get more complicated, we'll probably have to go out to bigger computers. But there's a lot of models. There's a thing called MESA, MESA, which is a program anyone can get to that models the sun. It actually models almost any size star. So if you're interested in a 10 solar mass star and what it would look like, you can pull up this program and it'll show you what it looks like.
And Henry, a follow-up, what size hard drive do you have on that laptop of yours to be able to conduct this kind of research?
You may have a partner here.
Yeah.
All right. No, I don't know. I have the latest Dell laptop, top of the line. So I don't know.
Couple gigs.
Yeah.
No, probably 10 to the 9, 12.
Can you cloud compute it? Can you store it up in the cloud?
Yeah,
as
you
a
can, but,
backup?
right. There's all sorts of ways of people are doing this. I mean, I remember right now my modeling isn't that sophisticated, but I remember many years ago I used to do SETI, and they had a community thing where you could download the
Screensaver?
the screensaver
Yeah.
and it would analyze stuff for you. And that still goes on. There's actually a nice site, I forgot the name of it, where you can go on there and there's all sorts of citizen scientist stuff going on where they want you to use your screen saving time to run programs for various things. And I know they have all sorts of stuff they're looking at, you know. And some of them in astronomy, some of them in other fields. So that help is all around.
Thank you.
Just need a giant X-ray beam to get to your white dwarf that's crystallized, so it's crystal structure off.
Yes, exactly.
Yeah.
I need it, but I need like a couple receivers at the right angle.
Yes.
I like it. Could you arrange for
Yeah.
an gamma ray star to shine on my?
Yeah.
I like it.
Cool. Are there any final questions? Online or in person? Cool. Well, if not, again, Henry, much thank you. That was real excellent. I don't know that we've ever quite had a talk like that before. So that was really cool.
You guys were
Yeah.
into or not into?
Yeah. So again, that concludes our meeting. Again, there are refreshments, so if people are up for it, continue to hang out. Otherwise, per usual, keep an eye on the groups.io. Come and join us during any of our Tuesday astronomy workshops. Otherwise, I hope we'll see you guys at our December holiday party potluck swap meet. More information to come on that. Take care, everybody.
Good.